We're going to walk through an example where we're going to be solving a system of first-order linear differential equations for the case where we have distinct real eigenvalues. We're going to find the general solution to the system of equations dx dt is equal to x plus 3y and dy dt is equal to 4x plus 2y. The first thing that we're going to do to solve this system of equations is to write the system in matrix form. We're going to let vector x have the components xy. This enables us to write our system like this. We have d dt of xy. And then on the right-hand side, we are going to separate the constants from the x and the y, and we're going to write it as a matrix 1, 3, 4, 2. Let me go up here and show you where that comes from. There's the 1. We have the 3, the 4, and the 2. And then we multiply this by x times y. This gives us the linear system. The derivative of vector x with respect to time is equal to what we call a matrix A times vector x. And we'll write down that matrix A is equal to 1, 3, 4, and 2. The next thing that we want to do is find the eigenvalues. To do this, we need to solve the equation determinant of a minus lambda I is equal to 0. Alternatively, we can solve this equation, lambda squared minus the trace of matrix A times lambda plus the determinant of A is equal to 0. I'm going to solve it both ways so that you can see how each works and then choose the one that's going to work best for you. We have our determinant, and then we're going to subtract off lambda from our diagonal elements. So this is going to give us 1 minus lambda, 3, 4, 2 minus lambda is equal to 0. When we find the determinant, we multiply the main diagonal elements, 1 minus lambda times 2 minus lambda, and then we subtract off the off diagonal elements, which is 3 times 4, and that's equal to 0. This gives us lambda squared minus 3 lambda plus 2 minus 12 is equal to 0. So we have lambda squared minus 3 lambda minus 10 is equal to 0. Now, before I find lambda, let's go over here to the right, and I want to show you how we're going to get the same equation using the trace and the determinant. This gives us lambda squared minus the trace of A. Let's go back up here and let's look at this. If we look at matrix A, the trace is going to be when we add the main diagonal elements. So this is going to be 1 plus 2 times lambda, and then we have the determinant of A, which is going to be the main diagonal elements multiplied, so that's 2 minus 3 times 4 gives us a minus 12, and that's 0. So we get the same equation, lambda squared minus 3 lambda minus 10 is equal to 0. I think this is easier, but the hard part is you have to remember this equation right here. Let's go down here and let's go ahead and let's factor this. We can factor this as lambda minus 5 and lambda plus 2 is equal to 0. So this gives us lambda is equal to 5 and lambda is equal to minus 2. I'm going to let lambda 1 be equal to 5 because that's the biggest eigenvalue and it's called the dominant eigenvalue. And then I'm going to let lambda 2 be the other one, which is minus 2. Now, before we go to step 3, we have to look at these eigenvalues and note what type they are. These are distinct real eigenvalues. Knowing this is going to enable us to choose the correct form for the solution. Step 3 is to find an eigenvector associated with each of our eigenvalues. To find the eigenvector, here's what we're going to have to solve. We're going to need to solve the system A minus lambda I times our eigenvector V is equal to 0. Let's just put from our previous page, our matrix A was 1, 3, 4, 2. And I am going to let vector V, just to make things easy, be equal to AB. Let's go ahead and let's set this up in general. We have A minus lambda I, so this is going to be 1 minus lambda, 3, 4, 2 minus lambda. You're just subtracting off lambda from the main diagonal entries. And then our vector V is AB, and it's going to be equal to the 0 vector. Now we're going to go ahead and we're going to find an eigenvector associated with each eigenvalue. Let's first let lambda be lambda 1, which is equal to 5. So this gives us 1 minus lambda, so this is 1 minus 5. We have 3, 4, 2 minus 5 times AB, and that's equal to 0, 0. This reduces to minus 4, 3, 4 minus 3 times AB, and that's equal to 0. You can solve this using linear algebra, but I'm going to solve it using just regular algebra in case you haven't had linear algebra yet. The system becomes minus 4a plus 3b is equal to 0. That's our first equation. And then our second equation is 4a minus 3b is equal to 0. Notice that these two equations are the same. So we're just going to go ahead and we're going to solve for one of them. And we get a is equal to 3/4 times b. Now what we have to do is choose a value for b so that we can also get a value for a. That's why let's go up here to the top and look at something. Do you see this word "and" right there? It says find an eigenvector, not find the eigenvector. The reason it says that is we are going to choose a value for b, and there are an infinite number of values that we could pick. And that's why there are an infinite number of eigenvectors. And we just need to find one. I'm going to make this as easy as we can. So what I'm going to do is I'm going to let b equal 4, and that's going to tell us then that a is equal to 3. That way we don't have fractions in our answer. This gives us that vector v, that's our eigenvector. We're going to call it vector v1 because this is going to match our eigenvalue lambda 1. And remember, it was equal to AB, and we now know that this is equal to 3 and 4. I'm going to highlight this because we're going to need this in a minute. Now we're going to find our second eigenvector, so we're going to let lambda be lambda 2, and that was minus 2. We're going to be looking right here, and lambda is negative 2. So we're going to end up adding 2 to the diagonal entries. This gives us 1 plus 2, 3, 4, and then 2 plus 2. This multiplies AB. It's a different AB than we had for our first eigenvalue. And we get 0, 0. This gives us 3, 3, 4, 4 times AB. And it's equal to 0, 0. This gives us the equations 3a plus 3b is equal to 0. And then 4a plus 4b is equal to 0. So this is the same equation. And we get that a is equal to minus b. I'm going to let b be equal to negative 1. And that means that a is going to equal 1. I just like it when the first entry in our vector is positive. I just think it makes it easier. So v2 is equal to ab, which we now know is 1 minus 1. And we'll highlight that. Now we come to our last step. That is to write the general solution. Because we have two distinct real eigenvalues, our general solution looks like this. Our eigenvalues are up here in the exponent, and then our eigenvectors are right there. Our general solution then is x of t is equal to c1 times v1. Let's go back up here. v1 is 3, 4. Times e to the lambda 1. Lambda 1 was 5, so that's 5t. And then we add on c2. Our v2 is 1 minus 1 times e to the lambda 2t, and lambda 2 was minus 2, so we have minus 2t. And there's our final solution. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.